Thank you, Mr. Sharma. Tower buildings are usually cylinder structures very sensitive to vibrations. During last years, there is a growing interest in the technical literature about simple models which can be useful for preliminary analysis on their wind and earthquake actions. For instance, lateral load effects on tall shear wall structures can be dealt with numerical finite element models or semi-analytical approaches. Finite element models are not in question for veritable design, but semi-analytical approaches can be often very useful in terms of structural global behavior and from an interpretive point of view of the global behavior of a structure. In this field, we are also have experience about elastic analysis of three-dimensional shell-type buildings using an internal constraint beam. But since the technical interest is often addressed to warping influence, it seems useful to work also on unconstrained beam models. Then this paper, this presentation, starting from a fine three-dimensional model, to formulate, the objective aim is to formulate a coarse one-dimensional warpable linear model able to simulate the bending torsion of the building floors with the addition of suitable distortional variables. The outline of the presentation is starting from a structural model of kinematic descriptor through a rational approach to derive the equation of the motion, the interpretation of this equation as a generalized one-dimensional continuum, and the qualitative analysis for a particular kind of cross-section, and finally a first example of application. The kinematics is quite simple. In the figure, there is a generic floor, is described by four parameters, two translation, a twist, and AK represent in general a warping amplitude, is different for different floor, and the warping function is assumed the same for all the floor of the building. In general, it is possible, in the spirit of Galerkin's technique, to use a number, M number. I'm sorry, it's not very good the resolution, and a number of warping function. And it is possible through a simple kinematic matrix to have a relationship between the displacement of the generic floor and the displacement of generic columns on the floor. Then it is possible to derive the elastic potential energy from the generic column, and using a simple continuization rule, it is possible to describe the elastic potential energy for the column as a function of over five parameters. The first derivative of the displacement U0, V0, and theta, and the warping amplitude A, and the first derivative of warping amplitude A prime. It's possible also to give a description about the elastic potential energy of the generic floor, for example, using a model of shear and deformable plate, and using continuation rule is possible to arrive to write in as a function of the AZ. AZ is the amplitude of the warping. Then, with a summation about the number of columns present in the building, and a summation with the elastic potential energy of generic floor, is possible to describe the energy density of equivalent beam and the elastic potential energy of equivalent beam. The kinetic energy is a simple description, is represented, and if a beam axes are centroidal and the space field is continuizing as done before, it's possible to describe the kinetic energy of equivalent beam. The work of external forces as a simple description, since we assume that the forcing act directly on the longitudinal beam axis. Using extended Hamilton principle, is possible to arrive to the 4 equations of motion in the variable. There are variables about the u0, the displacement in x direction of the floor, v0 in the y direction, the twist theta, and the amplitude of the warping A. M is the mass of the beam, and I is the inertial mass moment, and I psi is the warping inertia. It's interesting to give some comments about the coefficients in the motion equation. In particular, you can find the coefficients Kx and Ky F are total flexural stiffness of the beam. K theta is the total torsional stiffness. X, Y, F are the coordinates of the center of the flexural stiffness. And the stiffness with the apex W represent a contribution of the warping function. The contribution may be linear through the derivative of the warping function or quadratic. In particular, it is possible to note that the K1 coefficient has a contribution of the energy of the plate, and this coefficient may be positive or also negative if the contribution of the plate is particularly strong. And the second coefficient K2, there are a contribution of extensional of the columns. I think maybe is some interest to interpretation of the model as a generalized one-dimensional continuum. In particular, is it possible if the displacement are the free displacement before described, and considering A distortional variable, and exactly in the meaning that Professor Luong has explained this morning, and the main reference is the recent book, Mathematical Models of Beam and Cables. The strain are linearized, and also it appears the generalized strain alpha is equal to A and beta is equal to A prime. Using the virtual power principle, is it possible to the quality of internal and external powers satisfy for any kinematically admissible virtual motion to obtain the balance equation. In particular, it's interesting to note that appears two internal action D and B, which can be called distortional by distortional stresses, dual of distortional strain rates and their spatial gradients. Q small can be referred as the distortional force, that is the Lagrangian external forces associated with no rigid motion of the cross-section. And in order to formulate a constitutive law, we have to use the energy density function of the equivalent beam obtained before from the fine three-dimensional model as a function of generalized strain. Then, by equating the linear density of the formation work to the differential of elastic potential, is it possible to obtain a very simple relationship using a law similar to the Green's law, for which is it possible to obtain the elastic matrix where all stresses and strain are coupled. To try to give some qualitative explanation, you deal with the special case of a double symmetric section. In this case, also the warping function has a special symmetry properties. In the figure, you are the representation of modal shapes from a commercial finite element code about a simple building with only one floor. In this case, you can distinguish between two different behavior. A flexular warping, that is in this case the warping function psi shows a symmetric and skew-symmetric axis and simulates the floor bending in the fine model. And the torsional warping, that are distinguishing two different contributions. In both, the warping function show skew symmetric axis, and the floor contribution simulates the floor bending torsion in the fine model, and the column contribution simulates the column extension in the fine model. This is a classical contribution similar to the Vlasov model, and in our particular case, we are considering in the following square section, this contribution is absent for the spatial symmetry of the section chosen. In particular, when we are using a flexural warping function, the equation of motion are coupled in only one displacement and the distortional parameter A. For example, coupled in U0A or in V0A. In the case that are presenting in the following, in the last part of the presentation, considering the torsional warping function about floor contribution. In this case, the equation of motion are coupled in the rotation, in the twist theta, and in the distortional parameter A. But this is the simple expression of the equation of motion, and also it should be noted that the warping inertia is very small. It can be neglected in the passages. As a particular remark, this particular case we are considering the floor contribution to the torsional warping function finds a warp different from that described by the classical Vlasov theory, where the warping causes tangential stress just because of this variation along the axis and non-uniform torsion. This is a representation of the model, of the linear model, neglecting the warping inertia, and this is a non-dimensional form. In particular, the representation depends from the parameter K0, K1, and K2, depending from the ratio between the stiffness from the warping function and the torsional stiffness. And that is a possible analytical expression for the warping function. It is very similar to the warping function file from numerical program, numerical code. It's possible to find a closed-form static solution, for example, for the simple case of distributed torsional along the axis of a beam. The beam can be considered, for example, a cantilever beam. In this case, the characteristic equation is factored. This is a general solution, and this is a particular solution. It's possible to find the four constant from a boundary condition. Some numerical example. The first case presented is exactly the case of the numerical simulation through the commercial code. These are dimensions used. In this case, the three parameters K0, K1, and K2 are all positive. And the situation is when the number of floor is increasing, one is a trivial case, 5, 10, until 40 floor, is it possible to see that the twist at the top of the building is increasing. That is a shape of warping amplitude, and the shape is as this characteristic shape, and the maximum is reached not exactly at the top, but towards close to the top. When I try to change the thick of the plate, is it possible to find a particular case when the K1 parameters is almost zero? In this case, the situation is strange, it's a bit strange, because the twist tends to zero, and when the number of floors is increasing, also the twist at the top tends to become small. And also the shape of the warping is changing because the value of the parameters tends to become zero at the top of the building. And finally, using a thick floor, a relatively thick floor, is it possible to find a different sign for the coefficients of the ratio of the stiffness. In this case, the the twist tends to increase relative to first case, but in any case, when the number of floor is increasing, the twist at the top becomes small, while the shape of the warping amplitude is similar to the previous case. As conclusion, we are presenting a first step of linear analysis about a monodimensional generalized model of a macrostructure, useful for qualitative or preliminary analysis of micro three-dimensional models. Preliminary qualitative analysis, in particular case of symmetry, are shown. The corresponding static solution are presented. Some short-term prospects of this work are to complete the static analysis of the one monodimensional generalized model through a complete magnitude analysis of equation coefficients for a different case of the ratio of stiffness, analysis of the distortional by distortional stresses, and a complete comparison with numerical solution also when the number of floors is increasing, and analysis of different warping function, recovering also the classic warping due to column extensibility in the fine model, for example using a rectangular section, and increasing the number of distortional parameters in the spirit of generalized beam theory. And after the static analysis, to deal with a dynamic solution, for example, the free vibration and elastic action which can be acted on the building. Thank you very much for your attention.
So questions? Who wants to talk about buildings? Yes, sure. When you increase the size of the buildings, did you move from shear to bending beams?
If the behavior of a building is more shear, yes, I think yes. Now I don't study exactly at the moment the global behavior, but I think our beam is mainly a deformability like a three-dimensional shear type, but also we adding the deformation of the floor. Then is a three-dimensional shear type with a bending of the floor. But at the moment, another interesting point is to study also an effect like Vlasov warping is absent because our first example was too simple to add this.
Would it be possible to consider the columns that also goes in terms of supporting?
Only.
You have to consider columns for the floor, and what would be changed if you, instead of considering columns, you consider walls?
Walls. I think the formulation is not too different. It's a possible generalization. Yeah. I think it's very interesting because from also technical point of view, the warping of the walls may be influenced very much the general behavior. Yes.
Question here?
I've seen that you can consider also the extensibility of columns. And I wonder if in this case you have to consider also the bending of the homogenized beam. I mean, if you have extensibility, if you allow the columns to be extensible, to an extension, so you could have also flexure, I think.
Probably yes. Probably I think our model mainly is able to catch the shear behavior, but probably it's possible to have also a bending effect.
Okay.